Welcome back to Conquering the JavaScript Interview, the series that helps you decode even the trickiest of interview questions. In today's pun-tastic episode, we'll be mapping over our way through some isomorphic strings, which I'll explain in just a moment. A concept that's sure to leave you charmed. Get ready to deep dive into bijections, character mappings, and code solutions, because by the end of this here video, you'll be stringing together the perfect response to any isomorphic string question that comes your way. So grab your keyboard and let's untangle this mystery together. So, isomorphism, right? So, again, it's a function we're going to be writing here, our algorithm for today. Isomorphic strings write a function that takes two string arguments and returns a Boolean value on whether or not the strings are isomorphic. So egg and add are true, paper and title are true, but foo and bar is false, and ob and are false. So, looking at our outputs here, for those that know what this is, you already have an idea of where this is going to be headed code-wise. For those of you that have no clue whatsoever, things are a little bit trickier than just going, well, I kind of see what this is going on here. So let's try and actually explain what we're going to have going on when it comes to isomorphic strings. And I actually am going to switch my recording type here to my actual desktop and not just VS Code, because I have a new little tool to try and help me display this without having to resort to drawing diagrams beforehand. We're going to freehand it with some on-screen recording here, but yeah. So first off, isomorphic strings are strings that have a one-to-one correspondence between their characters while maintaining the same structure or pattern. So that's like the technical definition, right? Essentially, it's like two strings that could be that have characters that could be mapped to each other one to one, including not repeating a mapped over character. So the classic examples you always see online across all these overflow posts and Reddit posts and just different tutorials of this particular solution I kind of perused over are egg and add. That first one we see up yonder in this particular video, right? That in this particular input of getting true, how do these actually isomorphically map to each other? Let's actually break it down and take a look. So we have the characters E, G, and G. Oh, that's bad. Freehanding it was a mistake, boys and girls. This is a terrible one. And we also have add. All right, this is very professional looking. So the mapping of these characters, right? We have to make sure that the first character of E and A can be mapped to each other and one-to-one swapped without any issue whatsoever, right? So it has to be A is mapped to E, and then E is also going to be mapped to A in order to produce the words and make them isomorphic, right? So what we got going on here then is the letter G, and then that has to be mapped to the character D, and the same has to be true in the reverse, that D is mapped to G. Now, because G is now mapped to D, we cannot remap G to something else, right? So far we have a map that says, hey, all E's must become A's in order for this to be isomorphic. If E is supposed to be mapped to anything else in the character swaps, then we already have a problem. Then we're going to say that G is mapped to D. And so long as G is always D in our character swaps, then this string combo, these pair of strings, are isomorphic, right? That way, if we replace the character of E to A, so basically it'd be a swap, that would become, why did this become so much thicker all of a sudden? I don't think I hit a combo for my line tool here that made it too thick for some reason. Whoopsie. But the point being that these character maps like this cannot have letters going to other things. Like G could not also be something else, which we'll see in our next example here. But yeah, basically the idea is we need to take our letter A, and or our letter E, because it's mapped to A, they would then one-to-one correspondingly swap, and then this would become an A, this would become an E. then all G's would become D's, and then all D's would become G's. So these are, in fact, isomorphic strings because I can swap their character placements one-to-one without remapping any characters, right? G doesn't automatically map to something else here. Like, for example, if this was ADE instead of ADD, like if this was an E over here, we'd have issues because, well, this G is mapped to D already, and G cannot also map to E, which means these strings would no longer be isomorphic there, right? So, yeah, that's kind of like the breakdown I wanted to give y'all on isomorphic strings to kind of understand them a bit more with a little visual aid here of my lovely drawing tool. Okay, so now let's take a look at an example that doesn't map the way it should, which will be our example that we had of foo and bar. These do not map one-to-one to each other, right? So again, like when I first came across this a long time ago, I thought it was just like, can you move like the characters one-to-one and recreate the word? And I was like, well, duh, yeah, that makes sense, right? So we know that the F would map to B in this particular case because that's what this character map would be, right? That's the character association we're looking at right there. And then from there, we would have our O map to A as we go down the line here for our one-to-one character swaps, right? But now all O's have to be A's, right? But that's not the case because as we get to the third and final character of our mapping here, this would have to say that O now maps to R, which we know is not the case because we've already said O maps to A. So if we get this logic right here in our character map when we're trying to do this isomorphic test, O is already mapped to A, it cannot be mapped to R, which means these are not isomorphic strings of each other, right? So that is where the test would fail in this particular case, right? So another cool one to take a look at is paper and title is one you'll see regularly online as well. There needs to be a fast way to erase all this stuff. There we go. Right? So we can take a look at trying to write freehand. I should have just done comments. I feel like I could draw like a bash ASCII diagram just as easily as I could by handwriting this here. This is what I get for trying to freeball it, y'all, and not trying to make a diagram beforehand that I click through. Anyway, so paper and title are isomorphic strings of each other. Now that we know and understand the rules of do's and don'ts to isomorphism, again, that one-to-one correspondence and a character map, we can take a look at it here and say, okay, the P will map to T's. And remember, that must be true for the whole mapping for this to be isomorphic, right? So the P will be mapped to that T, and we're good to go. Then the A will map to an I, so we can swap it around. It's one-to-one so far, no problem. We get a P. Now the P is already mapped to T, and it's not going to get broken for the one-to-one correspondence because, well, it would map to T here, which we already have thumbs up taken care of right there in our current character map, so these are still isomorphic. Then the E would map to the L, and then the final one, the R, would map to the E at the end. Now, again, this is not a bad isomorphism. This is not a false isomorphism right here because E is mapped to L and R is mapped to E. That is not going to be a problem because E is not being mapped to two different characters, right? It's a different kind of shift there compared to what we're looking at in the foo and bar example. Yeah, and then the reverse is also true for this character map, and that's what makes it isomorphic, right? The T's will map to P's, the I will map to an A, the L will map to an E, and then the E will map to an R, and that's how we end up getting a true isomorphic test case in this particular example here. So remember, the point is you look at the correspondence of each character to make sure that they can correctly swap positions with a character in the other word, and you have to also make sure that character maps aren't repeated like they were in the foo and bar example. So with all this in mind, let's actually think about how we're going to solve this one here and how we're going to start approaching this one. So I kept talking about mapping characters over, and from my previous videos, if y'all been watching them, y'all know when I talk about maps, great way to do that is with objects or some kind of hash map or something like that, right? So that's what is going to be a crucial one in solving this, right? So we're going to think about it. we're going to have to clearly compare the strings, because first off, if they're not the same length of each other, then we can go ahead and cut it short there, because they cannot be isomorphic if they cannot do a one-to-one character swap, which means if their lengths are different, there's no point in continuing. So we can actually code that in easily and quickly here by simply saying if the length of string 1 does not equal the length of string 2, then let's just abandon ship early, because there's no way they're going to be isomorphic. So let's say quick test. If they're not equal length, they ain't isomorphic. Isomorphic. There. I can spell. Who said I couldn't? Yeah, so that's what we're looking at right there, right? Quick, easy, early escape to make sure that that we're not going to have any false positives, for example, here, right? There's no point in iterating through our strings or comparing characters, because clearly, like I was right there, like pretend I was using pen and paper to write out my character map and to compare the number of characters to both the strings I was looking at, like foo and bar, egg and add, paper and title, etc. We saw that I was kind of like drawing out a character map, and technically I should have been drawing two at the same time for comparison's sake, but we were going letter by letter, and that to me sounds like our good friend the for loop. Some kind of iteration is going to have to occur across the strings to make sure that their character maps build out uniquely and to one, right? So this quick little check right here is an easy way to abandon ship and not even bother with the iteration to save ourselves some computing power. Right on. So from there, we're going to have to initialize our character maps. This is where we're going to have an object. I'm going to code it choose to do it this way, where we have an object that will be each character map, right? So just like I was drawing a moment ago, we're going to have one map for the first word, a second map for the second word, and we can compare them to make sure they have the same keys and values. That way we know that they are isomorphic, because if they don't have a match, or if some letter has to get reassigned somewhere, like in the foo bar example, then that should be a return false, because these are not isomorphic, because the character O can't be mapped to two different characters like A and R in the foo bar example. So that's what these two objects are going to be, are kind of like hash maps to dictate what characters we've seen and to make sure that they map over to the other word correctly without any kind of remapping, right? Like I had mentioned, we're going to have to be looping through these two strings here. We've already even made sure that they are of equal length, so it doesn't matter which one we pick, but we're going to be using index positions, because if you're a newbie here, don't forget, strings work off the same zero-based index that arrays do, so we can modify characters or look at individual characters in strings by using their index positions and a square bracket syntax, just like you would an array. For any student coming out of here from our Covalence Full Stack Bootcamp, you remember this technique from the Just My Type lab. So we're going to have just going to pick string 1 because of the same length. It doesn't really matter. We're going to iterate by one letter, one character at a time by using i++ for our for loop here. Okay, so for some code, not brevity, but like readability, rather than writing string 1 square bracket I and string 2 square bracket I, let's just make a temporary variable that represents that so we can more easily visualize what we're doing here when I begin starting to mess with object properties and things like that. So remember, this square bracket syntax is for strings and their zero-based indexing that look like array syntax, right? So remember that. This is a string syntax you can do. Next, we need to then compare if the characters don't have a mapping yet, right? So if the characters don't have a map for map 1 and map 2, we need to create them. So we're going to do that by saying the following. If map 1 doesn't have a character mapping for the first char in the first string, let's create one, right? So again, this square bracket syntax, just for my newer students here, don't get confused. This is not array or string-based zero indexing. This is using the square bracket syntax of objects, right? So we have dot notation that we could do if we know what the property is going to be, which, name is not a property of the char1 map or map 1 like that, right? That dot notation. But we could also provide a string inside of square brackets to be a dynamic way of checking for properties in an object, right? So that's what we're doing here. This is an alternate to dot notation that allows us to do so dynamically with a variable, aka char1. Just keep that in mind. So And also, if map1 char at property char1 doesn't exist, then its value comes up as undefined. We know undefined is false, opposite of false is true, which will trigger this statement to then fire the conditional logic we want here. The logic being, take the map1 object, add that character as a property, and assign char2 as its value, because that's what that map is supposed to go to. Remember when I was drawing like the character map? The letter in the first word, arrow, the letter in the second word. Those are going to be our object properties and their values like I was drawing on the screen a moment ago. So that's what's going to happen there, and we're going to have to do the same thing for the second map, right? If map2 at char2 for the second word, the first letter of the second word, or string, doesn't have a mapping in the other object, we will also do the same thing. We're going to say, add that character to map2, and its mapped character in the first word is char1, like that. So now that we've added it to the object, as we are looping through, all we need to do is to check and make sure that the character 1 in map1, if it doesn't equal char2, or if the map2 char2 does not equal char1, then we're going to return false because they're not a match, right? So basically, we're looking at the mappings to make sure they match here. So we're going to say if, this will be a return false, if we happen to get a problem here. It's going to be comparing both of our character maps to make sure some letter hasn't been remapped incorrectly. So it's going to be two statements. The first statement is going to be if map1 at key character 1 does not equal character 2, that means we have an issue because they're no longer a match. We're going to do the exact same thing in map2 at char2. If it is not a match to char1, that means we have a mismatch in our maps, which means it's not an isomorphic string anymore. Again, like if O mapped to A in the foobar example is fine for the first time, and the next time we're going to get an O, mapped to an R in the foobar example, then we have a problem. It's not going to be a match anymore, therefore we're going to return false because this is no longer isomorphic. If we iterate through this whole thing, we should be able to get return true at the bottom of this function here. If the whole thing is iterated and a false has not fired off beforehand, that means we've gotten through both character maps. Everything has mapped as a one-to-one correspondence with no remappings of characters, which means if we got this far, it should be an isomorphic string, and we're going to return true from our function, right? So, as a breakdown once again, it's going to check the lengths of the strings to make sure they are equal. If not, unequal length strings cannot be isomorphic, so we stop early. We're going to initialize our two map objects right here, so we can start collecting character correspondences between the two words. It's going to store those mappings like we drew out and have been discussing. Then we're going to iterate through each character by using this for loop and this square bracket syntax that strings get to utilize that are kind of like arrays. And if the characters don't have a mapping yet, we're going to create one. This is where we take that pen and paper or that blue marker I had on my screen a moment ago and write out, like an egg and add, E maps to A. G maps to D. We're going to do that for the first character map and the same for the second character map, right? If the mappings don't match for a given character pair, the function returns false, which is what this is here, right? So E to A to E, no problem. G to D, D to G, no problem. G to D is the same thing. It exists already. We're good to go. And then D to G exists already. We're good to go. And it passes the test, right? That's how egg and add end up being isomorphic, right? Or paper and title. Or that paper and title, that's what I had here. But foobar do not, and here you can see very easily that A, B, and AA do not because A is mapped to A, okay, whatever, and then B is also mapped to A, or A is also mapped to B for the second one right there, and that's not good. We can't do that. A is already mapped to A, in the character map 2, so when we get to the second letter, A, it says, oh, I'm going to also map to B. That's a mismatch, which means it would return false here. But if it gets through that whole mess, then the strings are going to be isomorphic, and we're going to return true. So, yeah, with that breakdown right there, hopefully it works, right? So, let's check it out. let's go ahead and call a couple of these and see what happens. Console log, since I didn't add a console log anywhere in my code, we're going to do it this time. So save away. Yay, we got true. Let's go ahead and try paper and title. I do have a Mocha and Chai test file ready for this, so we can also test it that way really quickly. Let's change the arguments here like that. Save the file. We got true. Paper and title are indeed isomorphic. Then we're going to do foo and bar, the classic example right here of a false isomorphism. Yay! And then we'll do AA and AB, which we know cannot be isomorphic. And bravo, folks, we have succeeded in writing a little function right here. And I had the same thing for some tests that we can run as well. Oh, it's not test, it's test. My bad. Yay! Right, so again, like I wrote the same Mocha and Chai test for the console logs we just visualized here. We did some quick testing over here to actually run our Mocha and Chai tests over here to make sure it passed the tests I wrote for it, right? So, yeah, like isomorphic strings are pretty dang cool, I gotta say, right? So I felt really cool when I figured out how to solve this one, and, you know, if you're having a tough time understanding isomorphism still, like, hit me up in the comments if you find a video that really helps explain it better than I did, which again, like I'm not saying I'm perfect, you know, I'm doing it to the way I understood it and the way I think I can explain it to other individuals pretty well. Remember, it's about mapping, being able to swap character positions between two words in a one-to-one correspondence that makes them isomorphic. And yeah, I mean, if you had to think of an analogy for this, because normally I throw out analogies for my, you know, algorithms that I've been doing for y'all in this video series to help understand how we're going to go through it. In this particular case, I figured that because isomorphism was a pretty tough concept to understand on its own, rather than throw out a analogy of how this solution works, we kind of just thought about logically what isomorphism was, where we said, well, if they're not the same length, that doesn't matter. I drew those letters and their character maps out to get y'all start thinking in the term of objects, since this is one solid way to solve this one here. Then we had to compare characters, so we knew that meant we needed a loop, compare the characters, add them to the object maps, and then make sure that the maps have a one-to-one correspondence without remapping a pair somewhere. So this is where we check the pair of characters to make sure they're not remapped somehow, right? That way we don't get an O mapped to an A and an O mapped to an R, because that would be a mismatch pair, which would return false. So, yeah, if I had to give you, if you were thirsting for an analogy, because I know different people learn different ways. Some people are very hands-on with their learning. Some people have to understand like a theory before they can begin applying it and learning it. If I had to give you an analogy, imagine you're organizing two parties. Party A and Party B. They represent our two strings, right? They have an equal number of guests, so it's got to be isomorphic already, because if they had unequal guest lists, we would already have an issue there, right? There wouldn't be isomorphic parties. Each guest from Party A has a unique partner from Party B. Party A uses code names. Party B uses real names. So our task is to find if the two parties have the same guests using their code names and their real names. Right, so we would start by checking if the number of guests in party A and B is the same, because if they're not, they can't be isomorphic parties, which means, nope, we can go ahead and mark this one as big ol' X. We're done here. We would then create two empty guest books, which are our objects or our character maps that I've been describing. One for Party A, another for Party B. These guest books will help us keep track of the guest name mappings to the code name to the real name, so we can keep track of them all, right? From there, we would then go through the guest list for Party A and B, comparing code names and real names of each guest pair. For each guest pair that we're looking through on our guest books here, if the code name in Party A hasn't been recorded in Party A's guest book, I add an entry with the corresponding real name from Party B. If the real name in Party B hasn't been recorded in Party B's guest book, I add an entry with the corresponding code name from Party A, which is what this little tidbit represents here. Basically going through my guest book and making sure that my real name is mapped to a code name, and then my code name is mapped to a real name to make sure this is going through the way I expect, right? If the code name in Party A's guest book doesn't match the real name in Party B, or if the reverse is also true, if the real name in Party B's guest book doesn't match the code name in Party A, I can conclude that the parties don't have the same guest, which is what this code right here is saying, right? If the code name doesn't match the real name or the real name doesn't match the code name, we have a mismatch. We can conclude they are not isomorphic parties. If you get to the end of the guest list without any mismatches, you can conclude that the parties have the same guests, which is what this return true ultimately does for us in this weird little analogy, right? Right, so this is what we do. We just check for isomorphism between two strings. The strings are the guest lists. The characters in the strings represent the code names and the real names. The objects are the guest books that store the character mappings. We iterate through them and make sure the mappings are consistent for both strings. If there's a mismatch, we know they're not isomorphic. If we reach the end, we can presume they are, right? So yeah, hopefully this has been a fun one for y'all. I know it was fun for me to try and figure out a clean-ish way to try and explain how it works. Our big O complexity for this one, folks, is a big ol' O of n. Because basically we only do one iteration because the strings are the same length. We don't have to do any kind of nested loops, shenanigans, or sorting, or things like that. We're going to loop through our strings one time. We're going to be creating objects as well that will grow as the length of the input grows. So this is a time and space complexity of big O of n, which is that big linear line, if y'all recall, is the linear line. So the bigger the input n gets, the more operations we'll have to do. So our operations will simply just grow with our n, right? So, and worst case, let's see, the lookups and assignments for the object character mapping and the objects is an average time complexity of 1, so they don't really significantly impact your complexity no matter how big they are, right? Space complexity, also big O of n, because we have to store mappings for all the characters in both strings. So the bigger they go, the bigger our space gets, because those objects mappings will grow with that, right? So in terms of why this one is cool, you'll see this in natural language processing, determining if two words or phrases share a similar structure. You can help identify patterns. So you'll see this in NLP, natural language processing. Graph theory, isomorphism is a study determining if two graphs are structurally identical. You'll see this a lot in like social network analysis. There's graph theory in like chemical compound analysis, network analysis, that kind of fun stuff. As always, these kind of fun, this is a graph, Luke. These kind of fun algorithms are fundamental concepts that are done in cryptography. I feel like all these goofy algorithms I do are useful somewhere in cryptography. Isomorphisms can be employed in the design of cryptographic schemes and protocols. And algorithms like hiding the structure of the underlying data by transforming it into an isomorphic form that's difficult to decipher without a proper key, right? So basically, if we know how we isomorphically translated it without giving them the first guest book or party list, and it's really hard to translate, party B back to party A if we didn't have party A to compare it to. So that's a cool thing you could do in cryptography. It's in also data compression and computer vision, right? So identifying patterns or objects in video streams is what isomorphism can be cool for. So yeah, I mean, that's just, again, I'm been trying to also include where something like this would help you outside of an interview, because I feel like that makes it more compelling to learn crap like this, not just to pass an interview question and look like a cool kid with a cool job, but also to know that, hey, this actually does have some implications in the real world as a fundamental concept. So as always, thank you guys and gals for watching. I hope you found this video helpful in our journey to become better developers. If you enjoyed it, consider liking and subscribing. And as always, drop a comment down below if you have an alternate solution. There is an array-based solution I've seen on this one that I really chose not to go with because it was really goofy looking. But if you have a more performative one or an alternate one that speaks or resonates more to you, or like I said, have a video that has a better way of showing off what is isomorphism than my nice little drawing I did for y'all. Remember, keep comments positive and constructive, because we're all in this discussion together, helping each other grow. So thanks again for tuning in, and I'll see y'all in the next video.